profile projector is one of the optical instruments in the metrology lab, which can be used for inspection as well as measurement. It's a multi-purpose optical device that can be used either for the inspection purpose or for direct measurement. Profile projector consists of a optical system that is used for projecting a magnified shadow of a small object onto a screen, so that direct measurement can be made on the screen, or it can be compared with standard profiles so as to make a comparative assessment. Okay, let us see the construction of a profile projector. Profile projector is an optical device. Basically, it is used for obtaining a magnified shadow of a small object. So its optical system consists of, say, a light source. Through a condensing lens, it is falling on a directing prism, from which, passing through the object kept on a palette here, it falls on a reflector, and then it is, after multiple reflection here, falls on a screen, so that a sharp focused image, shadow of the object is obtained on the screen. And this shadow can be used for direct measurement or can be used for comparison with the standard profiles of the object, of which the desired parameters can be measured. And this is very convenient when the object, because of its size and geometry, which cannot be conveniently measured by conventional measuring devices. So the profile projector, the major units of a profile projector is, first is the optical system. So the optical system consists of a source of light, so this can be switched on from the mains. Actually, the switches must be here, and in that the fan must be switched on first, and then the telescopic light here, because the cooling is required for that. So this is right now it is not functioning, so directly connected to the mains only. So the optical system consists of the light source and a deflecting prism inside, which deflects the light rays upwards through the transparent glass palettes on which the object can be kept, and to the reflecting system consists of 3 reflectors, one here, one behind, and the third up, and finally one to the screen. So it consists of an optical system with a ground glass screen for obtaining the shadow of the object here, and a holding and positioning system for the object. So object can be directly kept here on the palette or between centers, depending upon the size and type of object. So here this holding screen, transparent glass screen, 2 stages are there, X and Y, fitted with micrometers for measurement. Now in this lab, profile projector is mainly used for the measurement of screw thread parameters, gear parameters, and some of the angle measurement, radius or curvature measurement, etc. So due to the restrictions of size and geometry of a component, if it is not possible to measure directly by conventional measuring instruments, any physical parameter that can be measured conveniently by projecting a magnified view of that feature on a screen, and the measurement can be made on the screen. So that is the working principle of profile projector. Now here we use this for the measurement of one, radius of curvature, and second, taper measurement. Or taper angle. Third, screw thread. Screw thread parameters. Of course, engineering methodology is mainly the measurement of length only. Angle also can be expressed in terms of length. So for radius of curvature, So when it is required to measure the radius of curvature of a curved profile, like this, a small piece. So this is the center. This is by measuring a chord length and its height. This. If you consider any chord, length of the chord and height of the chord, that is a perpendicular height of this or perpendicular distance of this chord from a tangent. So it can be measured anywhere. But on a profile projector, it has got two palettes or two stages for positioning the workpiece. So okay, the specimen can be kept on the transparent glass table, which are provided with 2 micrometers for crosswise movement as well as for longitudinal movement. So with these two movements here, you can measure these two parameters. So when a curved object or the specimen is kept on the table, you will get an image of that, mostly like this. So this is the projected image on the screen. And on the screen we have 2 cross wires or cross lines for reference. And here, while radius of curvature measurement here, the specimen must be kept on the table in such a way that the horizontal cross line is tangential to this. So we can make that horizontal cross line tangential to the projected shadow of the specimen here, so that a reading can be taken here, say let be R1. That means the first reading on the, say here we have a micrometer here. So this is 1 micrometer in this axis for the crosswise movement of the table, and thereby the shadow of the object will be moving up and down here. And similarly we have the second micrometer here for the longitudinal movement of the table, and hence longitudinal movement of the shadow on the screen. So the shadow can be moved crosswise as well as sidewise or longitudinally with these 2 micrometers, and the movement can be measured. Now in order to get the radius of curvature here, we position the shadow in such a way that the horizontal crosswise, or after obtaining the shadow, a sharp image of the object here, you make 1 crosswire, the horizontal crosswire, exactly horizontal and tangential to the shadow here by tear and error. So this is very important because we have to get the perpendicular distance as h. So on a circle here, the center, and we are considering the chord perpendicular to this. So this angle must be 90 degrees, so that this distance is h, and we take this distance as e, so that this is r. So if this is r, this is h, this distance is, it is r minus h, so that we can get r square is this distance is marked e. This is a by 2 then. So this r square is equal to a by 2 whole square plus r minus h the whole square. By expanding and rearranging, you can get r is equal to a square by 8h plus h by 2. So this is the formula in your manual. So radius of curvature is calculated using these 2 distances here. This is a and this is h. In terms of these 2, radius of curvature can be measured. For that, we are positioning the crosswire tangential to the shadow of the curved specimen here and taking the first reading here. So that is R1. Then move this micrometer so that the shadow is brought down or the crosswire is moved up so that it come to this position. Actually it is not by moving the shadow down here, this palette is moved here by this crosswire here, so that crosswire is taken there. So this is the second reading, R2. So difference between these two readings will give the distance h. This distance is obtained. So this is h. Now leaving this micrometer or the position of the palette at that position here without disturbing that. Now move the second palette, longitudinal movement. So this micrometer is operated here so that the crosswire is taken to one side. So here, so this is R3, reading number 3, and the same way it can be taken to the other side. Say here, it is R4. So the difference between the reading R3 and R4 obtained from this micrometer here will give the distance between these 2 points, and that is nothing but the chord length. So we have got the length of the chord as well as the height. Using the substituting those 2 parameters in the equation, we can calculate radius of curvature. So while doing this experiment, the important points, the specimen must be kept on the table and positioned while obtaining that sharp image. This must be positioned in such a way that the horizontal cross line is tangential to this, and say this distance is a by 2 and this is a by 2. This is because the palettes can be moved in 2 directions, mutually perpendicular directions, crosswise and across that or longitudinally. So while measuring the chord length, it must be perpendicular to this. So for measuring the radius of curvature of a given specimen, a curved specimen here, first you place the specimen on the transparent glass plate, and this handle can be used for obtaining a sharp image of the object. So this is for vertical adjustment here, so that a sharp image can be, a focused sharp image can be obtained on the screen. Then position the crosswires, vertical and horizontal crosswires, such that the horizontal wire is tangential to the specimen. Take the first reading corresponding to this position on the micrometer. So this crosswise movement micrometer here, take one reading here. Move the shadow downwards to the next position here and take the micrometer reading as the second reading here. So this can be moved to any depth. So actually we are making a measurement on a chord, length of the chord and its height from the curve. First reading is taken tangential to the shadow here. Move the micrometer further so that the shadow is brought down. The second reading is taken, and now move the palette. The longitudinal movement is used for taking the third reading on one side. So this is the third reading. Move the micrometer and the palette in the opposite direction so that the reading on the other side is obtained. So this is reading number 4. Now the difference between reading number 3 and 4 will give the length of the chord, and the difference between the reading number 1 and 2 will give the height of the chord. That is, first reading is A and the second is H. And from the formula, R is A square by 8 plus H by 2, can calculate what is the radius of the curvature. While making this measurement, the two important things to be remembered is the first reading must be taken tangential to the curve here, and then it is to be moved down to a distance such that the two extremities are within the range of the micrometer. So micrometer's range is only 25 millimeter here, so that the depth chosen here or the specimen placed on the pallet is such that when you move it horizontally, this must be within the range of the micrometer. Next, for the measurement of taper or taper angle. You know, taper is defined by conicity, the term conicity. So this is capital D and this is small d, and this is the distance between the two diameters L. And the taper is defined by conicity K, that is d minus d by L, or the half taper angle, that is defined by tan alpha is equal to d minus d by 2L, where capital D is the diameter, the larger end, and small d is the diameter, the small end, and L is the distance between the two sections or the axial length it is. So, in order to measure the taper angle, so it is enough to measure diameter two sections of a conical object and the distance between the two sections. Now this can be done on profile projector. So when a large conical object is, or conical specimen is to be measured, so which is not possible by other measuring devices like micrometer or vernier caliper directly. So support this specimen, given conical specimen, between senders on the profile projector table. Now, one important thing to be remembered while mounting the workpiece is that the senders or the axis of the specimen must coincide with senders of the axis of the senders. That means it must be horizontal and parallel to the table surface. Otherwise, if it is slightly inclined here, you may not get correct reading. So when it is when the axis is parallel to the table surface or coinciding with the axis of the senders here, so the projector shadow will give the exact diameter. So in that case, on the profile projector, mount this conical specimen between senders and get the enlarged shadow of the specimen here. It is something like this. So this is the shadow obtained. So between senders. Now, the same way we have two micrometers so as to move the reference line crosswise and longitudinally. So here on the screen we have the cross lines provided with 1 micrometer here and second micrometer here. Now another thing is, so this micrometer is having a limited range only for the micrometers here. Now this is a larger specimen here, so you have to take two readings to get one diameter. Suppose you are taking one reading here and correspondingly one reading on the other side here. So the difference between the two reading will give the diameter here. But when you position this one here, the micrometer is to be moved so that the crosswire is moved or the shadow is moved across the crosswire here. So it must be within the range. Now at any suitable position here, you can position the crosswire. Say here, let it be the first position, reading on 1. Corresponding to this position of the crosswire here, you take the first reading on the micrometer here and record that as reading 1. Now move this crosswire to the other side by operating the micrometer here, so that the second reading is recorded here as R2. Now the difference between these two readings R2 and R1 will give the diameter across. This diameter. So that is our diameter. Now move this one to another section and measure the diameter here also. Now once you move this one here, you will not get the length between the two sections here. So without altering this position here, you record the reading on this micrometer here and take that as the first reading for the length. So this is R3. So this micrometer is not disturbed now. Crosswire is here, and here itself on this micrometer, second micrometer on the longitudinal axis, record the third reading, that is the initial reading for the length. Now move this micrometer to the new position here. Say camera to the next section. This distance, and so it comes here. You can move it up or here itself. So this is R4. This reading is R4, and difference between R4 and R3 will give the length between, or the distance between diameter D and larger diameter and the smaller diameter. Now again move the crosswise parity here, or the first micrometer here, to position the crosswire at this position. So this is R5. So at this position, record the fifth reading as R5 and move the crosswise micrometer so that the crosswire is moved to the other side again, and this is R6. So difference between R5 and R6 will give the diameter at this section. So here we have measured the diameter at this section as larger diameter D, and we have measured the diameter at this section as smaller diameter D, and the distance between these two sections is here, that is L, the distance L, that is nothing but R4 minus R3, or R3 difference R4 depending upon the position. Difference between R4 and R3 will give the length. Now substitute in this equation in order to get the taper angle. So this is obtained, this is obtained, this is obtained. So find the half taper angle alpha from the equation from these parameters. So profile project also can be used for measurement of taper angle. So I have mounted a conical specimen here between centers here, so that the taper angle can be measured using profile projector. So similar to screw thread, the taper specimen also, which is mounted between centers, must be positioned such that the image or the shadow that we are getting on the screen must be within the range of the micrometers. So move it forward here so that we can position somewhere here. So the horizontal cross line is here. Now this crosswise micrometer is in its starting position only at the beginning of the range. So keep the image slightly below the horizontal line. Let it be here. And this micrometer is also under its initial position here. So opening, it will move to the right. So let it be there. Now here, further check the sharpness of the image. Okay, it's a good image now. Now move it upward here. So the cross lines can be used for taking the reading. Now the intersection of the horizontal and vertical cross lines, so that coincides with a point on the surface of the image. Now this reading can be taken as the first reading. Reading R1. So move the cross lines to the other side of the shadow here. So move it further. So here the micrometer is open here. So the cross lines are brought to the other side of the shadow here. So this is the position. for the second reading. So at this position, record the second reading, and the difference between these two readings will give diameter of the specimen at that position. Now, in order to measure the taper, we are measuring the diameter of the specimen at two different positions and the distance between the two. So we have measured one diameter here now. Now the cross lines can be moved to another position by moving this micrometer here. But before doing that, take the reading on this longitudinal palette micrometer here and the third reading. So the whatever reading is there on this micrometer, that is recorded the third reading for length measurement. Now move this further. Let us move it to the right. So it is shadow is moving to the left. So we have brought it to another location. Say here, stop here. Say at this position here. Take the reading on the longitudinal micrometer here at the fourth reading here. This. So the difference between the third and fourth readings will give what is the length. So that is the fourth reading. Now to measure the diameter at this section, say the crosswise movement is used. So the crosswise micrometer here, take this as the fifth reading, or the initial reading for second diameter measurement. So this is the fifth reading here, and move the cross lines to the other side. Closing it. So the micrometer has come to its limit at this section here. So this is the this reading 1, 2, 3, 4, 5, 6 readings. Now this is the sixth reading or the second reading for the second diameter. Take the sixth reading here. So difference between fifth reading on the first side and the sixth reading on this side. So these two will give the diameter at the second position, and the difference between the third and fourth readings will give the longitudinal distance between the two diameters, that is the axial length. So from which we can calculate the taper height. Now here also, while positioning the image for taking readings here, see that the readings are possible within the range of the micrometer. So the axial length, after taking one diameter, when you move to the next section here, the length must be chosen in such a way that the diameter there is within the range of the micrometer. That is the important point to be remembered. And the third measurement is the flank angle. So in order to measure the flank angle of a screw thread, flank angle cannot be measured directly here. You can measure the thread angle, and half the thread angle is flank angle. So flank angle is this angle is flank angle. Now here, so we have the cross wires. So make that cross wire to coincide with one flank. So we have the mutually perpendicular cross wires here. So make one cross wire to coincide. Rotate the screen such that one of the cross wire is made to coincide with a flank. Corresponding reading on the protractor. So the profile projector screen can be rotated, and on the rim of that screen, a protractor is marked. It's a vernier protractor with degree reading, and on the vernier minutes reading. Now here, when the cross line is parallel to or coinciding with a flank of the thread corresponding to this position, you read the angle theta 1. on the protractor, take the reading theta 1. Then the same wire can be moved. Move the screen in the opposite direction so that the same wire is brought to the brought to coincide with the flank on the opposite side. So the angle between these two positions on the cross line is nothing but the thread angle. Now when it is moved to the second flank here, corresponding to that reads the angle theta 2. Now the difference between these two readings, theta 1 and theta 2, will give the flank angle, the thread angle, and thread angle by 2 is the flank angle. So this is thread angle, flank angle is theta by 2. Similarly for the measurement of screw thread parameters, so screw thread can be fixed here between centers. So while fixing the screw thread between centers, you have to ensure that it is held in such a way that the axis of the thread is parallel to the pallet. Axis must be horizontal. So for measurement, the screw thread can be mounted between centers here on this pallet here, and this holding unit can be slided on the pallet here crosswise so that it can be positioned in such a way that while taking measurement, the object shadow will be within the micrometer range. So the micrometer which is fitted with the pallet is having only 25 millimeter range here. So in the during measurement we can move it only through 25 millimeters. So the positioning of the object is important. Otherwise it may fall beyond the range of the micrometer here, so that you cannot measure. So adjust this parity here so that it is within the range. So now I have mounted this screw thread within the centers here, but it is not brought to the projector range. So in order to position it at the right place, you can move this parity here on the table here. So when it moves here, see the image is coming. It is completely moved. Now to position this correctly so as to take the measurement here, so here the micrometer is having only 25 millimeter range here, and in this crosswise micrometer here it is fully closed now. The reading is 1 millimeter or a half millimeter, 1 millimeter. So that is at the initial position it is. Now while moving the micrometer here, see the movement of the image is like this. So in order to make the measurement, say major diameter here, say one reading on this side and the next reading must be on the other side. For that I have to open this. So for the initial reading here, you place the shadow of the screw thread somewhere here. So it is now the beginning of the reading here, and you can lock it now. Now I have positioned it for the measurement. Now the image is not very sharp. Make the image sharp by focusing it. Okay, now we have got a fairly sharp image of the screw thread. Now in order to make the measurement here, adjust the micrometer so that the horizontal cross wire is parallel to the threads. Say this screen which is having two cross lines, a vertical and a horizontal one, you adjust the horizontal cross line so that it is brought parallel to the threads, say more than 3 or 4 threads here. Now fine adjust the micrometer here so that the cross line is on the thread. We can take the reading on this micrometer as the initial reading for the major diameter. So the present, what is the reading here? That is the initial reading or the first reading. Now move the micrometer or open the micrometer further here so that the image or the shadow of the screw thread moves to the other side. So the cross line is brought to the other side of the screw thread. So the horizontal cross line is brought parallel to the threads on the other side, and here we can record the second reading, reading number 2. So that difference between these two readings will give the major diameter of the screw thread. Now for the measurement of minor diameter or the root diameter, the screw thread here, the same cross line can be brought to the root of the thread. So this is it. So the horizontal line is, this cross line is brought to coincide with the root of the thread here, and this reading can be taken as the third reading. And after that, move the micrometer further so that the cross line is taken to the root diameter on the other side. So this is, so the same cross line is made to coincide with the root of the thread on the other side. So this is the fourth reading. Now the difference between reading number 4 and 3 will give the minor diameter or the root diameter of the screw thread. Similarly, to measure the pitch, for pitch measurement we can make use of the vertical cross line. So for that, now the measurement is on the other parallel. So here the shadow can be moved longitudinally by moving this micrometer here. So pitch is say from crest to crest or root to root. Say a reading on one thread and move it to the next thread here. But since the crest of the thread is not very sharp, it is either a radius or a truncated crest here, it is very difficult to position the cross line exactly at the identical position. So for that, what we can do is, you move this screen with the cross line so that one of the cross line can be brought parallel to the flank surface of the thread. Say like this. Say a cross line is made to coincide with the flank surface. So here you take one reading. If required, you can refine the shadow and adjust the cross line. So take the first reading for pitch. So first reading on this second micrometer here, and after that move the same cross line to the next flank. See here. So here this is the second reading for pitch. So difference between these two readings will give exactly the pitch of the screw thread. Now to measure the flank angle of the screw thread, flank angle is half the thread angle. So we can measure the thread angle here. So for that, you choose one of the cross lines here. Let the vertical cross line is not at the root of one thread here. Position here. Now this scale is having this ground screen. This is having a protractor here engraved in degrees. So the angle measurement can be made on that. So make one of the cross lines and rotate these screens such that one of the cross line is brought tangential to or parallel to the flank on one side. So it is adjusted and brought parallel to the flank on the left side. Right. Now on the protractor here you can read the angle. Have this 60, 70, 75, 78. It is 78, and here the vernier is there, which is one division is 1 degree. So this is a 78, nearly 79, 50 degree. So 50th one is coinciding with the main scale. So one division is 1 degree here. So it is a 78 degree 50 minutes it is. First line to the other side, so as to bring it parallel to the flank on the other side. Here. So So it is brought parallel to the flank on the other side here. Now the reading is it is a 137 degree, which is the coinciding division, nearly 58. So the difference between these two readings, so this is the second angle reading, theta 2. So the difference between these two readings will give the thread angle. So thread angle by 2 is the flank angle.